All right, in section 5.3, we're going to talk a little bit about diagonalization. Now, we already have seen diagonal matrices. So basically, a diagonal matrix we've seen before, it has real numbers on the main diagonal and then zeros elsewhere. We're going to talk about, well, mostly square matrices here. Well, in fact, all square matrices. But in this case, we have a 3 by 3 diagonal matrix. Now, diagonal matrices are really nice for a couple of reasons. First off, they're really easy to multiply with. Go ahead and see what's going to happen when you multiply the diagonal matrix 4, 0, 0, 0, 3, 0, 0, 0, negative 2 times this matrix. And then see what happens when you multiply the diagonal matrix by itself, let's say 3 times. Push pause on the video and go ahead and do that. All right, so here's what I got with that. When I took 4, 0, 0, multiply it times this matrix, again, 4 times 1 is 4, plus 0 times 3, plus 0 times negative 3. That just gives me 4. 4 times 2 gives me 8. The others will be 0. 4 times 0 gives me 0. So notice that what happened here is that basically the first row of this matrix here just got multiplied by 4. You can see really quickly that what's going to happen is that when you take 0, 3, 0 multiplied times this matrix, the only thing that's going to happen is the second row of that second matrix is going to be multiplied by 3. So you're going to get 9, 18, negative 3. And then when you take 0, 0, negative 2, that last row gets multiplied by a negative 2. So you get 6, negative 8, negative 10. So a diagonal matrix, really nice to multiply by. If you're multiplying on the left by the diagonal matrix, we're just taking each row and multiplying it by the diagonal entry in the row itself. Okay? Now, if you cube a diagonal matrix, well, think about this. I'd have to multiply the first row of, again, think what we just did. First row, 4, 0, 0, multiplied by first column here, 4. You'd get basically what's going to happen is you're going to end up with 4 times 4, 3 times 3, negative 2 times negative 2. Or, in other words, this is 4 squared, 3 squared, negative 2 squared on the diagonal entries. If you do that a second time, what's going to happen is you're just going to end up with 4 to the third, 3 to the third, and negative 2 to the third on the diagonal entries. Okay? So basically what happens is if you multiply a diagonal matrix by itself a number of times, all you're doing is you're taking each entry, raising it to that power. Now, obviously, that does not work for matrices that are not diagonal. So if we do not have diagonal matrices, that property doesn't work. But with diagonal matrices, we get really, really nice multiplication going on. So we want to find diagonal matrices. And we're going to introduce the topic of similar matrices. We say that two matrices are similar if there's an invertible matrix such that PA, P inverse is equal to B. All right? So basically, if we can find an invertible matrix that I multiply the left by that matrix and the right by the inverse of that matrix, then what's happening, excuse me, is that A and B are similar. Now, the interesting thing about similar matrices is that they have the same eigenvalues, okay? So you can prove that. This is a little intense, but basically this is a slide that has a lot of writing on it. But you can go through the fact that similar matrices have the same eigenvalues. If A and B are similar, using what we just did there, B is equal to PA, P inverse. Well, how do we find eigenvalues? We find them by the characteristic polynomial, which is determinant of B minus lambda I. I can replace B by P A P inverse. Now, P A P inverse, I can write I, since P and P inverse multiply to give you I can write P times P inverse here. And if you want, you can factor out the matrix P on the left, and you can factor out the matrix P inverse on the right. So you get the determinant of P times A minus lambda I times P inverse. And what do we know about determinants? Well, we know that determinants, we can take the determinant of this matrix times the determinant of that matrix times the determinant of that matrix. And that gives me the determinant of all three matrices multiplied together. Now, determinant of P times determinant of P inverse, because those are just real numbers, those are going to cancel each other out. Those are going to be inverses of one another, and they're going to cancel each other out. And so you're left with determinant of A minus lambda I. And what that means is that the characteristic polynomial for B is going to be the exact same as the characteristic polynomial for A when it's simplified. So they must have the same eigenvalues. All right. Now I do want to make a note here. I'm saying that similar matrices are always going to have the same eigenvalues. However, the inverse is not true. There can be matrices who have the same eigenvalues, and that doesn't mean they're similar. All right, so just because two matrices have the same eigenvalues, they're not necessarily similar, but similar matrices will always have the same eigenvalues. All right. So what we would like, since diagonal matrices are nice, what we'd like to do is find out which matrices are similar to a diagonal matrix. So we'd like to see if we can create a diagonal matrix which is similar to the matrix that we're given. All right. And that's the idea of being diagonalizable. So a matrix is said to be diagonalizable if there's a matrix, if there exists an invertible matrix P such that A is equal to P times D times P inverse. In other words, A is similar to D, where D is a diagonal matrix. So that's the idea of diagonalizable. And when it asks you to find out if A is diagonalizable, what it's asking you to do is try to find the P and try to find the D. So find the matrix P and find the diagonal matrix D. Okay. By the way, equivalently, what we can say is that A is diagonalizable if we can multiply some matrix P and P inverse in this way to give me a diagonal matrix. So P inverse that way to give me a diagonal matrix. All right. So here's what we're going to do. We're going to show that A is diagonalizable with matrix P. And we're going to show that by just taking what we had in the previous slide, multiplying this out, and seeing that you get a diagonal matrix. So I want you to take P inverse times A times P and see that it does in fact give you a diagonal matrix. All right, push pause on the video and go ahead and do that. All right, so here it is. Oops, excuse me. We have what I did is I took my matrix P, I plugged it in my calculator. I took my matrix A, I plugged in my calculator, and all we have to do is do P inverse times A times P, and sure enough, we get the diagonal matrix 3, 0, 0, 4. So yes, our matrix is diagonalizable, and specifically you get the diagonal matrix 3, 0, 0, 4, and you get that using P inverse times A times P. All right. Now here's the deal. How would we go about this? How would we go about finding a particular P? All right. So we got to note what the matrix did in this last example. All right, this 1, 2, 0, 2. Well, you'll notice that A has eigenvalues of 3 and 4 because A is a triangular matrix. Note that when we dealt with the diagonal matrix that we got, 3 and 4 stood out. Also, you'll note that 1, 0 is an eigenvector with eigenvalue 3. So go ahead and check that if you take this vector 1, 0 and multiply A times the vector 1, 0, it has eigenvalue of 3. And moreover, 2, 1 is going to have an eigenvalue of 4. So again, you can check out that vector 1, 0 is a eigenvector with eigenvalue of 3, and 2, 1 is an eigenvector with eigenvalue of 4. So this P was basically just eigenvectors corresponding to each of these two eigenvalues. So that kind of leads us to this next theorem. It's called the diagonalization theorem. If we have a square matrix, it is diagonalizable if and only if that matrix has n linearly independent eigenvectors. Moreover, if we have if it is diagonalizable, then P is going to have the eigenvectors as its columns, and the diagonal entries of the diagonal matrix D are going to be the eigenvalues. All right. And in the columns themselves, just like we saw here, when we diagonalized this 1, 0 this first column corresponded to eigenvalue of 3. And if you were to look at the matrix, the diagonal matrix we just found, the 3 occurred in the 1, 1 spot. All right. And 2, 1 had the eigenvalue of 4. So 4 occurred in the second column, in the 2, 2 spot specifically. So in other words, order matters. Okay, So whichever order you place the eigenvectors in, that'll correspond to the order that the eigenvalues show up in our diagonal matrix. Okay, so we have the diagonalization theorem. N by N matrix is diagonalizable if and only if we can find n linearly independent eigenvectors, and those eigenvectors will be the columns of our invertible matrix P. The diagonal matrix D will be the eigenvalues themselves. Excuse me, the diagonal entries of the diagonal matrix will be the eigenvalues themselves. Now, I'm going to ask you to diagonalize a matrix, and you might say, well, what does that mean? Basically, that means take an A and find P and find a D so that this equation is true. All right. Or equivalently, the other one we saw where you take P inverse A times P and get out D. But all we're really looking for when we ask you to diagonalize is to come up with the matrix P that we'd have to use and the matrix D that we'd have to use. So I want you to go ahead and diagonalize the following matrix. Find the P, which is going to be eigenvectors, and find the D, which is going to be a diagonal matrix with our eigenvalues. So go ahead and do that. Switched over to this now. So here's what we're going to do. We're going to try to diagonalize A. Now, as we saw, this requires us computing the eigenvalues and eigenvectors for each eigenvalue. So let's start by finding the eigenvalues. So take A minus lambda I, just like we did in the previous section. Find the determinant of that. That's going to be 20 minus 5 lambda minus 4 lambda plus lambda squared minus 6, if I've done this right. And then that means my characteristic equation, when it's simplified, is lambda squared minus 9 lambda plus 14. Set that equal to 0 to get the characteristic equation. You can solve the characteristic equation by factoring lambda minus 2 times lambda minus 7. That means that the eigenvalues are 2 and 7. Once you've gotten those eigenvalues, then for each one of these eigenvalues, we can create an eigenvector. In fact, we could get more than one eigenvector. We can get infinitely many, but only one in a basis for the eigenspace. By the way, notice that each one of these, 2 and 7, had multiplicity 1. All right. So 2 has multiplicity 1. We find this eigenvector. Again, row reduced echelon form A minus 2I. We're solving essentially the null space of A minus 2I. So x1 is here, x2 is free. So I let x2 be anything you want. x1 has to be negative 1 times x2. So there you go. There's an eigenvector for lambda equals 2. When you do 7, you go A minus 7I. Row reduce that, you get 1, negative 1.5, 0, 0. So the eigenvector is 1.51. Now what we have is we have two eigenvectors. Because they came from different eigenvalues, they have to be linearly independent. So all we have to do is say, yes, A can be diagonalized. What should the P be? Well, I take my eigenvectors and just put them in the columns of P. So this first one, negative 1, 1. put that in the first column. 1.51, put that in the second column. Now again, this isn't the only eigenvector we could have chosen. 3, 2 also works. Okay, so you could have also had this matrix P. There's a lot of other eigenvectors that work. Okay, just choose 2 instead of 1 as your free variable. I'll leave it there, just hopefully that doesn't mess anybody up. But the goal here is to see that had eigenvalue of 7. So 3, 2, since that was in the second column of P, and that one had an eigenvalue of 7, the diagonal matrix D in the second column will have 0, 7. And since negative 1, 1 had eigenvalue of 2, the first column of my diagonal matrix is going to be 2, 0. Now it's pretty obvious that the order matters. For instance, if we would have set 3, 2 as my first vector and negative 1, 1 as my second vector, then what would have happened is I would have had to swap the 7 with the 2. Okay, so all of these are diagonalizable and they yield the same A no matter which sort of combination, as long as we have it lined up right. As long as the 3, 2 corresponds to eigenvalue 7, and as long as negative 1, 1 corresponds to eigenvalue of 2. All right, so there you go. By the way, you can check that this works just using your calculator. So let me plug that in. I've done that, and I have plugged these things in. I should have, maybe I should have swapped the screen there, but that's fine. I took my matrix B, and I plugged in 3, negative 1, 2, 1, just like we did. D, let that be 7, 0, 0, 2. Now again, we go, so I used matrix B in my calculator as a substitute for matrix P that I wrote down. So P times D times P inverse is equal to 5, 3, 2, 4, which is my original matrix that I started with. Now, again, you can show that order isn't going to affect this by just taking your matrix. Let's swap out the columns. In fact, I'll swap out the columns. Instead of using 3, 2, I'll use the other eigenvector we found. That's 1.51. And notice negative 1, 1 now went for the first column. I'm going to have to change the diagonal matrix that I use. That's 7 is going to have to change to a 2, and the 2 is going to have to change to a 7 because I swapped what columns they're in. But regardless, now my new D, or my new, let's do B first. My new B is that one. My new diagonal matrix is that one. And when you take B times D times B inverse, you still get 5, 3, 2, 4. Okay? So as long as you choose, as long as you choose an eigenvector and an eigenvalue, your P, just put 1 in each column. Now I will say on online homework, I always choose the free variable to be 1. And as far as the which ones I go for, if you put it in wrong, try to swap your columns on your homework. So on homework, obviously the inputs matter. I always use the free variable as 1, so I wouldn't use this. I would use the 1.51 vector and this D. And again, if the order doesn't quite match up to what you have, try to swap the order and see that you get the right thing. Okay? All right. So I want you to try doing this one. Diagonalize the following matrix. Now, push pause and go ahead and try to do that. All right, hopefully you went ahead and pushed pause and tried to diagonalize this matrix. What we see here is that it is a triangular matrix, so the eigenvalues are going to be 6, 4, 1. So there's no real need to make a characteristic equation. We just get 6, 4, 1 as the diagonal entries. And so we can go with the 6, the 4, and the 1 separately and find an eigenvector for each of those eigenvalues. Now when you row reduce a minus 6i, you get this equation, excuse me, not this equation, this matrix, 1, 0, negative 5 thirds, 0, 1, negative 5 thirds. And what that means is that x3 is a free variable, x1 has to be 5 thirds times x3, x2 has to be 5 thirds times x3, and then obviously x3 can be anything we want it to be. We choose 1. Again, that will correspond always on Moodle. So 5 thirds, 1 is an eigenvector with eigenvalue 6. When we do lambda equals 4, we row reduce a minus 4i. We get this matrix. That means x1 has to be equal to 0. x2 has to be negative 1.5 times x3. And x3 can be free. So that's going to lead to the eigenvector 0, negative 3 halves, 1. Now, if you put this in decimal form instead of in fraction form, that's okay. If you wrote negative 1.5 and I wrote negative 3 halves, shouldn't be a big deal. Well, for the eigenvalue of 1, when you go a minus 1i, it row reduces to this free variable x3, but x1 has to be equal to 0, x2 has to be equal to 0. So our eigenvalue is 1, has a corresponding eigenvector of 0, 0, 1. Now, that means A can be diagonalized. What I would do is I would probably start with the 6 because that's sort of the first one that pops out. Not that you have to, but that's kind of commonplace. So 5 thirds, 1 is going to be our first column of P. Oops, excuse me. And that's going to correspond to the eigenvalue of 6. So we'll put 6, 0, 0 as the first column of our diagonal matrix. Then I go scroll back up. Eigenvalue of 4 corresponds to eigenvector 0, negative 3 halves, 1. So I put that in my second column. That had an eigenvalue of 4. And then lastly, eigenvector of 0, 0, 1 corresponds to eigenvalue of 1. Eigenvalue of 1. So if we let this be the P and that be your D, then we get diagonal matrix. And by the way, you can check this by plugging it into your calculator or any other way that you would like to check it. You can check it by hand too if you'd like. So there you go. A can be diagonalized. Now notice in both this case and the previous example, we had our eigenvalues which were distinct. In other words, they each had multiplicity 1. And we saw in the last section that you can always find a basis for the eigenspace, and that basis will have at least one vector in it. So if I have 3 distinct eigenvalues, I'm going to have at least, well, I'm going to have 3 eigenvectors. Since we started with the 3 by 3 matrix, that guaranteed enough eigenvectors to fill up my P. All right? So what I'm saying is essentially the following. If we have n distinct eigenvalues, then we know we can find the P because we're going to get one vector per eigenvalue. And that one vector per eigenvalue is going to represent one column of our matrix. And so we have exactly the right number of columns that we need. So if an n by n matrix has n distinct eigenvalues, then we know A is diagonalizable, and it's diagonalizable by using the eigenvectors as columns of P. Now what about this? Here, this is also triangular, so the eigenvalues pop out at us as 1 and 4. I want you to see what happens when you try to diagonalize this matrix. Go ahead and push pause and try to diagonalize this. All right, so when I went ahead and did this, obviously eigenvalues are 1 and 4. So I looked for the eigenspace when lambda equals 1. We row reduce echelon form A minus 1i. You get this matrix. Now this matrix has 2 free variables. And so what we can come up with are 2 linearly independent eigenvectors because we have 2 free variables. All right, these would have been the eigenvectors that form the basis for our eigenspace corresponding to lambda equals 1. All right, so we have these 2 eigenvectors. They form the basis for the eigenspace corresponding to lambda equals 1. We know they're linearly independent because they correspond to free variables here. Specifically, there's no x1, there's no x2, so x1 and x2 can be anything they want. And just like before, when you did 4, we'd come up with a single eigenvector for the basis of the eigenspace where corresponding to lambda equals 4. So what we got is we got 3 eigenvectors. And because they came from different eigenvalues, different eigenspaces, because these 2 corresponded to free variables, I know that those 3 eigenvectors must be linearly independent. So I have 3 linearly independent eigenvectors, and therefore my matrix A can be diagonalized with 1, 0, 0, 0, 1, 0, 1, 7/3, 1, and as my P, and then my D would have been 1 0 0 0 1 0 0 0 4. All right. By the way, just like in this one, you can sort of reorganize if you wanted to swap out columns. You could swap out, this third column for the second one. The second one would go to the third, and you just swap out these, this 1 and this 4. All right, so this one can be diagonalized. Now I want you to try the same thing for this matrix. Again, it's a triangular matrix. All right, hopefully you went ahead and did that. I'm going to go through this one. We take the matrix that we're given, 4, 2, 3, 0, 1, 7, 0, 0, 4. We see it's triangular, so eigenvalues are 4s and 1s. 4 has multiplicity 2 this time. 1 has multiplicity 1. Let's start with the eigenvalue of 1. If we try to find eigenvectors for that, what we'll do is we'll have one eigenvector in a basis for the eigenspace corresponding to lambda equals 1, and that eigenvector would be negative 2/3, 1, 0. Because when you put a minus 1 a minus 1 times I in row reduced echelon form, this is the matrix you get. So x1 has to be equal to negative 2/3 x2, x2 is free, x3 has to be equal to 0. Now, the interesting one is obviously the eigenvalue 4. When you take a minus 4 times the identity and put that in row reduced echelon form, what you get is this matrix. This matrix means that x1 is free, x2 has to be 0, and x3 has to be 0. So notice we only had one free variable, but our eigenvalue of 4 had multiplicity 2. So I could only find one eigenvector in the basis for the eigenspace corresponding to lambda equals 4. And what that means is that A cannot be diagonalized no matter what P I choose, because I don't get enough eigenvectors. I only have 2 eigenvectors out, and so I'm always missing that third eigenvector. So because I can only find 2 eigenvectors that are linearly independent, my matrix P is not diagonalizable. All right. So notice the 3 examples that we did. The first example, we had 3 eigenvalues. They were all distinct. These were from 3 by 3 matrix A. So all distinct, and therefore I could diagonalize it because each eigenvalue had a corresponding eigenvector in its basis. So you could diagonalize it that way. The second example I did of the 3 by 3 case, we only had 2 eigenvalues, but the eigenvalue of 1, which had multiplicity of 2, generated an eigenspace whose basis has 2 vectors in it. So multiplicity of 2, eigenspace had 2 vectors in it in the basis. Obviously, that led to our A being able to be diagonalized. And then the last example, we had this eigenvalue of 4, which had multiplicity 2, but there was only one eigenvector in our basis for the eigenspace. And therefore, we only generated out two linearly independent eigenvectors. So my matrix A could not be diagonalized in that case. So here's what we're saying. First off, if A is an n by n matrix, and it has less than n distinct eigenvalues. So in other words, if some of our eigenvalues have multiplicity bigger than 1, then sometimes A is diagonalizable, and sometimes you can't diagonalize A. That's pretty straightforward. And moreover, what we're saying is, in the cases where our matrix is diagonalizable, then the eigenspace for each eigenvalue has the same dimension as the multiplicity of that eigenvalue. All right? So if our eigenspace has dimension 2 and our eigenvalue is of multiplicity 2, then that's really good. If our eigenvalue has multiplicity 2, but our eigenspace only has dimension 1, then we can't diagonalize it. All right? So the multiplicities of the eigenvalues have to match up to the number of basis elements in a basis for the eigenspace. So let's take a quick look at a couple of examples, and we won't in this first one, we won't go through the entire finding the p, but I will sort of argue why something is diagonalizable or why it's not diagonalizable. So I want you to just take a moment, push pause on the video, and ask yourself if this matrix is diagonalizable. All right, hopefully you've caught on that this matrix is diagonalizable. If you look at the eigenvalues, 7, 5, 0, 8, they are all distinct. So we have a 4 by 4 matrix. We have 4 eigenvalues. They're all distinct, 7, 5, 0, and 8. Therefore, they're all going to correspond to having an eigenspace, and the dimension of each of those eigenspaces has to be 1. So yes, this is diagonalizable because we have 4 distinct eigenvalues. Well, how about this one? I want you to use minimal effort to determine if this matrix is diagonalizable. So go ahead and push pause on the video and see if you can do that. All right, hopefully you went ahead and did that. I know I did. So when I went to solve this, what would happen? Well, first off, I see that my eigenvalues are 5 and 2. Now, I can kind of ignore 2 for the question of, is this diagonalizable? Now, if I had to come up with the p, then obviously I'd have to look at 2, but 2 has multiplicity 1, so the eigenspace is going to have dimension 1 at least. So 2 is going to correspond to an eigenspace of dimension 1. That's sort of guaranteed. So the eigenvalue of interest is 5 because it has multiplicity 2. So if it can generate an eigenspace of dimension 2, then it can be then my matrix can be diagonalized. If 5 can generate an eigenspace whose dimension is only 1, then my matrix will not be able to be diagonalized. All right, so what we do is we take a look at lambda equals 5, row reduced echelon form, A minus 5i. We get this matrix. We've seen that before, and that's not a good sign. I only have one free variable, and so I only have one eigenvector in a basis for my eigenspace corresponding to lambda equals 5. So lambda equals 5 had multiplicity 2, but the corresponding eigenspace only has dimension 1, and therefore A cannot be diagonalized with any P. So it can't be diagonalized. I want you to do the same sort of observation using this matrix. I want you to see if this matrix can be diagonalized. All right, so we got 2, negative 4, 4, 0, 3, negative 1, and so on and so forth. We take a look at the matrix, and obviously the eigenvalues are 2 and 3. Because it's triangular, they're on the diagonal. 2 is the eigenvalue of interest because it has multiplicity of 2. 3 has multiplicity of 1, so we know it's going to generate an eigenspace with dimension 1. So 3 is good. 2 is the one we need to look at. Now, when you row reduce A minus 2 times the identity, you get this matrix here, which, by the way, has a free variable for x1 and also has a free variable for x3. So we end up with two eigenvectors, specifically 1, 0, 0, and 0, 1, 1, generating the eigenspace corresponding to lambda equals 2. So 2 had multiplicity of 2. That generates these two eigenvectors. I should say, so the dimension of the eigenspace is 2, and the multiplicity is 2. Obviously, my other eigenspace would have dimension 1, and 3 has multiplicity of 1. And therefore, A can be diagonalized. Or, in other words, A is diagonalizable. So the multiplicities matched up with the vectors in the basis for each eigenspace. So A is diagonalizable. We can find vectors 3 linearly independent vectors, 2 from this eigenspace, and then we'll be able to find 1 from the eigenspace generated by lambda equals 3. All right? So that's the big concept of trying to find out whether or not a matrix can be diagonalized, so whether a matrix is diagonalizable. And we see that the way to do that is to create this matrix P, which has the columns which are eigenvectors of our matrix. Okay, and if we can find enough eigenvectors, we can diagonalize. If we can't find enough eigenvectors, we can't diagonalize. So there you go. That is the end of section 5.3.